So how do we compute the visibility graph? The idea is to use a sweep line algorithm, but instead of a normal sweep line, we want to use a slightly different, a radial sweep line. In other words, you first shoot a ray upwards from this point that you want to compute all the visible vertices, and then you rotate it. So this is the first vertex that is visible, so you add it, then you rotate it until the next vertex. You realize that this is not visible, so you don't do anything, you rotate it, you hit another vertex, not visible, and so on. Okay, and this way, by just rotating it all around, we can find all the visible vertices in n log n time. So the claim is that, this seems very similar to sweep line algorithms, and you could probably figure out the details and so on, because some of the things look a bit different. But I would like to claim that this is actually identical to a normal sweep line. Why is that the case? And to show this equivalence, we're going to use projective plane. Essentially, the hint is that we want to rotate the ball of the projective plane until p is a point at infinity. If you remember the videos about the projective plane, there is nothing specific about parallel lines or about any point. Any point can be represented as a point and a sphere in 3D, and then by the mapping that I talked about in that lecture, that can be mapped to a point. So imagine that this entire picture is embedded in a 3D on the surface of a sphere, on a 2D ball. And that this picture is the shadows created by the projection that we talked about. Then just rotate the ball until this point P becomes a point at infinity. What happens then is that all these lines all these rays that emanate from P become horizontal lines or parallel lines, okay? And also rotated such that all the parallel lines are horizontal. Of course, the shadows change, and these obstacles also will create a different shadow. So this is essentially a geometric transformation that we're doing. What happens is that you'll get basically a picture like this. So now the point P is a point at infinity, and the rays are basically like this. The rays that come from either from the left or from the right. Those are the rays that come from this point P at infinity. So basically now what we want is that we want to find the visible vertices, or vertices that are visible from infinity at the left or infinity at the right. Now we can see how this can be done using a normal sweep line algorithm. Just run the normal sweep line algorithm, and the visible vertices are the minimum and the maximum x coordinates at any given point in time. So this can be solved in n log n time using a normal sweep line approach. So again, what about the rest of the algorithm? Well, the rest is very easy. After computing the visibility graph, we add, if we want to solve the shortest path from S to T, we add S and T to the picture. We find the visible vertices from S and the T. We add them to the visibility graph, and then we run any normal shortest path algorithm. For example, we can write Dijkstra for n squared log n time in total. So this is very efficient, and actually surprisingly this can be improved to n log n time, but we don't have time to discuss that.